Okay. Okay. So is the slide visible?
Yes, sir.
Okay, so we'll start the session now. This is material characterization tutorial 8. As for me, I am Sabyasachi Panda from Department of Metallurgical and Materials Engineering. So, in the last class, if we go through a little bit of recap, then we studied about the generation of X-rays, like how the X-rays are generated from a metal source or an anode or a target material, and then we went through the different scattering and absorption phenomena, and we have also gone through different diffraction equation that governs the X-ray generation and X-ray analysis. One of them was Bragg's equation, and another one was Lave's diffraction, and also how to visualize the Bragg's plane. We drew the Bragg's plane as mirror polished surface. Then, but how to know that which plane is giving condition for diffraction? That means which plane is the Bragg's plane. Then we assumed we went through the theory of Ewald. That means we went through the theory of a reciprocal space, and then from reciprocal space we got to know that how the means what is the physical how we can correlate the reciprocal space as with the real space using the Ewald sphere. That means the condition for diffraction is the points which will be coming on the surface of Ewald sphere. Those will be the giving us the condition for diffraction, and the points in the reciprocal lattice are the planes in the real lattice, right? So these were just give me a minute. I don't know what is happening. Just give me a minute. I don't know. Yeah. Yeah. So up to this much we have studied the condition of diffraction is when the the planes or the reciprocal lattice points come into the surface of a Ewald sphere. Then the condition of diffraction happens, and that is the condition. And the condition that we have seen for diffraction, if I am writing it here, the condition for diffraction is that the scattering vector should be equal to the reciprocal lattice vector. This is the condition for diffraction. Once you tell that this is the condition for diffraction, then you don't have to explain the background of the diffraction, like how the scattering vectors are coming, how the scattering vector is coming, and what is the reciprocal lattice vector, because from here we have derived that in the earlier in the last class, that scattering vector will be 2 sin theta by lambda, and this d is 1 by d. So from here we are getting eventually lambda is equal to 2d sin theta. So if anyone asks you that what is the condition for diffraction, you should say that when the scattering vector will be equal to the reciprocal lattice vector, then the condition of diffraction is met, and the equation is given by lambda is equal to 2d sin theta, or if you want to go for higher order reflection, then it is n lambda is equal to 2d sin theta. So up to this much we have studied. So now we will see, we'll go a little bit in depth into the scattering phenomena. We have studied that when the X-rays are incident on a material, then there are some amount of absorption happening, and also simultaneously some lots of scatterings are happening. So those scatterings are two types of scattering. One is incoherent scattering, another one is coherent scattering. So what do you mean by incoherent scattering? When there is no definite phase relation between the incident and the scattered radiation. So here I am not talking about the diffraction, I am talking about scattering phenomena. That means scattering can happen in any direction. So when the scattering phenomena will give rise to diffraction, when this phenomena takes place. So now I am coming back to know or to understand a little bit more of scattering. So the incoherent scattering, what is the incoherent scattering? When there is no the phase relation might be there, but that phase relation might not be constant over a period of time. If you are taking your incident beam and your scattered beam, there is a phase relation at time t is equal to 0, let's say, but that same phase relation might not be true when you are taking some time t is equal to t1. Similarly, so between all these time interval, the phase relation might not be constant, it might be varying. So when those things will be happening in scattering, the scattering process is known as incoherent scattering. And remember, this incoherent scattering is not beneficial to us as an when we want to analyze our material through X-ray diffraction. And what is happening in when the incoherent scattering takes place, the X-ray photons, they interact with loosely bound electrons here. So let's say this is my photon coming, and this is a loosely bound electron which is there in my material. Now what will happen? It will come and hit it, right? This is a, if I am writing, this is a photon and this is a loosely bound electron. Okay, so this is my first scenario. Then after collision, after the collision of this photon with my loosely bound electron, so this photon, let's say it is coming with this, here I have written hc by here lambda naught is not visible, so here hc by lambda, let's say my energy of my incident electron, my incident photon is E naught, that means hc by lambda naught I am taking. This is the energy. Now after hitting, there is another scenario which can happen, like this electron will be ejected somewhere, and what will happen to this photon? Let's say initially it will hit it, and then this photon will be here, and this is the intermediate stage. And when I am talking about the third stage, let's say the electron will be going in this direction, and my photon, which was this one, this is my photon which was coming with some energy, that energy is hc by lambda naught, it will go in this direction. If I want to take this direction, then this will be going in some random direction. I am taking this direction as 2 theta. It is not necessary that you have to always take the direction as 2 theta. You can take the direction as theta, you can take the direction as theta by 2, or also you can take the direction as 2 theta. Why I am taking 2 theta? Because to me it will be mathematically convenient when I am trying to calculate some trigonometric function, like here you can see one function is 1 minus cos 2 theta, then cos 2 theta can be easily broken down to sin theta cos theta term. So that is why I am taking that my scattering angle is 2 theta. Okay, so now coming to so let us say this is my first stage, this is my second stage, and this is my third stage. Okay, so in the third stage, what is happening? My electron, how my electron initially my electron was at rest, now my electron is moving. That means some amount of energy my photon, which was coming with hc minus lambda naught, it has given to this electron. That means my hc by lambda naught energy, which was earlier, this was the maximum energy which was earlier with my photon, now it has reduced. Now the reduced energy, let's say I want to measure, then that reduced energy is somewhat hc by lambda. So that means what I am saying it here, initially my the wavelength of my this photon, it was lambda naught, it is the initial wavelength. Okay, so this is lambda naught. Now after scattering, my final wavelength, let's say I am talking about final wavelength, then it will be lambda. And since I know that E naught here, right on top I am writing E naught will be greater than E. Why? Because E naught is the incident energy that my photon was coming with, and E is the amount of energy in the third stage. Here my photon is carrying after giving some amount of energy to my electron. If I want to quantify that, so here I am writing E naught will be E let's say plus energy of the electron. right? So this is how I can quantify the energy that that my photon, the total amount of energy that my photon is coming with. So now I know that E naught is greater than E. That means the initial energy of my photon is greater than the final energy of my photon. But here the energy is reciprocal to the wavelength. So from here, if I want to say something, that lambda will be greater than lambda naught. That means if I am losing energy, my wavelength will be longer than the previous wavelength. So that is why the lower wavelength your electromagnetic radiation is, the higher amount of energy. Since E naught is greater than E, that means my lambda will be, that lambda means the wavelength after the scattering. Lambda naught is the wavelength before the scattering. Here is lambda naught, and this is what I am talking about, lambda. So lambda is wavelength after the scattering and lambda naught is wavelength before the scattering. So here lambda will be greater than lambda naught. So if I want to calculate the, and this so here since there is energy change taking place for my incident photon, so this kind of energy change is happening, as well as what is happening here, the wavelength change is also happening here. Since my wavelength is getting changed due to interaction with the material, so this kind of scattering is called as incoherent scattering, or sometimes this scattering is called as Compton scattering. And so how much wavelength is getting changed here? So that wavelength change is given by lambda minus lambda naught. Lambda minus lambda naught is equal to h minus m naught c 1 minus cos 2 theta. So here you can see h is the Planck's constant, as we know. Okay, m naught is the mass of the material, mass of the object that is coming, and here c, you can see c is the velocity of light. Okay, and here 1 minus cos 2 theta, you can see 2 theta is the angle of scattering. From this equation we can see that h divided by m naught c, this will be a constant equation. If I take that, this m naught is the electron that are coming. Okay, if I assign some mass to this m naught, or if I take that another electron is coming and ejecting this electron which was initially at rest, then I can quantify this total term. So the expression would be lambda minus lambda naught is equal to some constant into 1 minus cos 2 theta, right? So this can be this I can do. So, and here you can, one interesting thing to note is that in the whole expression, this change in the wavelength is not in the change in the wavelength expression, there is not a single term of lambda or lambda naught. That means it is not dependent on the wavelength of the of my incident beam before or after the scattering. So only term which this term is incident is on this angle called 2 theta, or we should not say that this is 2 theta, rather we should say that this is scattering angle. So this is what known as Compton scattering. And remember, this Compton scattering will always give us the background, or the diffuse background which comes into our peak or peak intensity when we are doing an analysis of our material. So this is incoherent scattering. Now coming to the coherent scattering, what will happen to the coherent scattering is that in coherent scattering the wavelength will not change. In incoherent scattering, due to the loss of energy, the wavelength was changing, but in coherent scattering we shall always assume that the wavelength will not change. That means the energy will not change after the scattering phenomena. However, their path might change. The incident X-ray which is coming from this direction, their path might get deviated, their path might get they can directly transmit through the material, or they can scatter at some angle. However, their lambda will be constant in these cases. So if you look at here, let's say scattering of an unpolarized incident beam, this incident X-ray, now what I am assuming is that this incident X-ray is unpolarized. What is the difference between an unpolarized beam and an polarized beam? We have seen it in optical microscopy. So unpolarized means it goes in all sorts of directions, and unpolarized means the electric vector, if I am talking about, so the electric vector would be in all directions. So that is what the unpolarized beam is all about. While the polarized, or if you remember, linearly polarized, so in this case the electric vector would be aligned like this. So this is what, since X-ray is also an electromagnetic radiation, we shall consider the electric vector. So here also, if we are considering the electric vector, so the in one direction the vector should be aligned. So that is what called as polarized beam. But however, while generation of X-ray takes place, we are not sure that the electric vector are aligned in a particular direction. So that is why initially when we are talking about the intensity, then we must have to add a factor which takes care of the expression of unpolarized beam and converts it into the polarized beam. We'll see that how it takes place. So here what happens, the incident X-ray comes. You don't have to worry too much about this geometry. It might look a little bit complicated, but I'll explain this thing. So here E naught is the electric vector that I am talking about. So why we have taken the electric vector? Because we want to if we want to let's say we are talking about the polarized beam and then unpolarized beam. We want to quantify the X-ray radiation in terms of a wave. Why we are taking in terms of
Sorry, just hello.
yes.
Yes, could not connect. Can you please repeat it again? Polarization, some network issues is here.
Okay, polarization, the polarization and the polar. Here I was talking about that scattering can happen. Means when we are producing X-ray, we are not sure whether the beam is polarized, completely polarized, or linearly polarized, or it is unpolarized. So that is why here I was talking about the unpolarized beam where the electric vector was in all direction. However, here if I put a polarizer, which we have seen in optical microscopy, where we are using the polarized beam, polarized light beam, same thing we can also put in X-ray diffractometer. From unpolarized beam we can produce a polarized beam, right? And polarized beam means the electric vector would be in one direction, and since X-ray is an electromagnetic radiation, we have to consider the polarized beam for our intensity calculation. So that is why, let's say my incident X-ray is coming in this direction, and at O there is a scattering center. Okay, I don't know what scattering center is, whether it is electron, whether it is proton, whether it is neutron. I don't know whether it is an atom or it's a combination of atom or lattice structure. I don't know as of now, but O is a scattering center, I am assuming. Then incident X-ray, when it is coming, then at this point if I want to take any amplitude, then let's say this is the electric vector at this point, at the origin. Now after the scattering happens, after the incident X-ray interacts with this scattering center, it will go somewhere in this direction. At any point of time and at any distance, let's say I am talking about the distance of r. At any distance, if I want to calculate the amplitude, if I want to calculate the amplitude of my wave. Why I am taking a wave? Because a wave for me it will be convenient to take in a wave, to consider my X-ray radiation in a wave vector. Why? Because at any point I can quantify, or I can identify its position. At any point of time also I can know at what time my wave is propagating in which manner. So since wave will give me these two property, and so that is why I want to quantify my electromagnetic radiation in a wave vector, and so that is why I have taken here the electric vector. So here at the origin, if you see the resultant electric vector, so this is EO, right? And the resultant electric vector will be in terms of EOZ. That means if I am breaking this resultant electric vector here into two components, EOZ, EOX, right? I can break it similarly. After scattering of this incident X-ray, if I want to find my amplitude of the wave at point P, which is positioned from the origin at a distance of r, same thing I can do. I can break my resultant electric vector into two axes, EPZ, and similarly here EPX. I can break this thing. So after breaking all these things, but amplitude is not that much necessary for me, because ultimately I am getting what I am getting in my detector. I am getting the intensity. So we know that amplitude is intensity, the square of the intensity is the square of amplitude. So that is why whatever amplitude I am getting here by breaking this electric vector, right? So that intensity will be given by the scattering phenomena where my wavelength is not changing, and wavelength is not changing means the intensity which I am getting, that will be coherent scattering. Okay, so here if I take the EP as my amplitude, here you can see this expression you have to look at. You don't have to really go, if you want you can go through the components, like how the components have been broken, how the EP and E naught have been broken into EOZ and EOX, and then subsequently they have been converted to the intensity, and finally the total derivation, if you want to look into, you can go and look in any of the books. But what important for us is this expression. What does this expression tell? EP square. Remember, I am talking about amplitude square. That means here the amplitude is given by the electric vector, and P means at any point P. So I am talking about the intensity right now. So the intensity in and where I am talking about the intensity, I am talking about the intensity in coherent scattering. So what will happen? EP square, that means the intensity at any point P due to coherent scattering will be given by 1 by r square e to the power 4 divided by m square c4 into 1 plus cos square 2 theta by 2 whole into E naught square. So this expression actually looks like a complicated term, right? But if you carefully look at the expression, this expression has three parts. 1 by r square, this is one part. E4 by m square into c4, this is one part. 1 plus cos square 2 theta by 2, this is another part, and E naught square. E naught square is the intensity or the amplitude of the our incident. The E naught square is intensity of our incident beam. So here if I break down into 1, here 2, and here is 3. If you can see 1 by r square. So this r square, here the r is given by the distance from the origin or the scattering center where you are calculating your scattering intensity, right? Similarly, e to the power 4 m square c4, if you consider this one, then generally the scattering will see when the scattering will be occurring, E is charge of electron, here c is velocity of light, and m will be the mass of the mass of the scattered center. So here mostly the scattered center will be electron. Why it is electron, we will see. So this will be electron. Now if you put all these values together, this will become a constant, right? And this constant value is generally it's given generally if any questions are asked in this section, then this constant value is generally given. And then comes E naught square. We know that this is the intensity of our incident beam vector. Now 1 plus cos square 2 theta by 2. So what does this mean? So this value give us. So this is what I was talking about, the unpolarization to polarization. That means when X-ray beam is coming, it is coming in all direction. You cannot restrict the X-ray beam to come to a particular to come to a single direction. That is why you cannot restrict it to come to a single direction, because they don't have effective charge. So if they don't have charge, you cannot put an electromagnetic lens or you cannot deflect them without putting an object into their path. So that is why what we are doing, an unpolarized beam, when we are talking about how to convert our motto is we have to get the information, we have to get the scattering intensity from a polarized beam. So geometrically and experimentally, when people have calculated 1 plus cos square 2 theta, so this is called the cos square 2 theta by 2. This is called the polarization factor. Okay, so these are the three terminology that you have to remember while calculating the intensity by an electron. Intensity by an electron in coherent scattering. So if you see here, scattering by a single electron, now I talked about, I don't know what is my scattering center. Now I assign my scattering center to an electron, right? So if I assign my scattering center to an electron, scattering by a single electron is given by this equation. That equation is known as Thomson equation. Always remember, incoherent scattering is governed by Compton's shift, that delta lambda which I said, that is governed by Compton's shift, and coherent scattering is always governed by Thomson equation. Here if you see 1 plus cos square 2 theta. Now here what did I do? Here EP square I have written. Now I have changed this EP square into IE, right? That means the intensity that I will get from the scattering by a single electron, right? This will be given by IE 1 by r square, where r is the position from the origin or from the scattering center where I am measuring the intensity, and E4 divided by m square C4, 1 plus cos square 2 theta by 2, and here I naught, right? So, and if you remember, this e to the power 4 divided by m square C4, this is called as square of the classical electron radius, and this value is given as 7.94 into 10 to the power minus 26 centimeter square. Okay, what does it mean? That means classical electron scattering cross section, how much it will give you, the cross sectional, how much intensity it will give you from one electron. Now comes an interesting question. Let's say I am writing this thing, IE is equal to 1 by r square, and I am writing this value 7.94 into 10 to the power minus 26. So here you can see this is unit is centimeter square, right? And here r is given in centimeter. So here will be centimeter square in the denominator, here the centimeter square is in the numerator. So it will eventually cancel it out. So now let's say I am putting this value 1 plus cos square 2 theta divided by 2 into I naught. Now one interesting thing to observe it here. Now let's say my distance where I am calculating the intensity is 1 centimeter. I am putting some numerical value to this expression is 1 centimeter, okay, where I am calculating the intensity due to coherent scattering. That means my r is equal to 1 centimeter, okay, and let's say this expression cos square 2 theta value, maximum cos square 2 theta value, how much it can get? 1. And when this cos square 2 theta value will become 1, then what, let's say my theta, okay, I am putting another term into this, my theta is 0, okay, my theta is 0 means my cos theta is my cos 2 theta will also be 0. When my cos 2 theta is equal to 0, cos square 2 theta is theta is 0 means cos 2 theta will be 1, cos square 2 theta will be 1. Then this terminology I am writing it here, 1 plus this cos square 2 theta will be 1 divided by 2. So effectively this will become 1, right? Now if I want to put it here, this terminology I am writing it here, IE is equal to 1 by r square, r value I have taken as 1 centimeter, 1 by 1, okay, into 7.94 into 10 to the power minus 26. Here this terminology which is the polarization factor, that means 1 plus cos square 2 theta by 2, this value has become 1, that means this is also 1 into I naught, right? So effectively I am getting IE is equal to 7.94 into 10 to the power minus 26 I naught. Now you can observe how much intensity I will get when my intensity is calculated after at a distance of 1 centimeter, okay, 7.94 into 10 to the power minus 26. That means it is so much less intensity I am getting, but in reality we are getting extremely high intensity. So what is the case that we are getting high intensity? Because if I am measuring my intensity at a distance of 1 centimeter and I am taking that so theta is equal to 0 means, you can understand, theta is equal to 0 means my beam is almost transmitted beam, it's a direct beam, I am not taking any scattering currently, and there is no partial interference. So this is the maximum interference which is happening, and I am getting so much low intensity. So that means will my but in reality I am getting, when I do an X-ray analysis of my sample, I am getting so many high intensity I am getting. So what is the case then? Here one thing to notice is this IE what I have taken, it is the scattering, the intensity of the scattering by a single electron, okay. when you are talking about, let's say, a mole of electron, in a mole of electron there will be n number of electron. N belongs to the Avogadro's number. So all those electrons, if you consider, let's say if I am in a perspective, if I am giving in 1 molar volume, if I am considering in 1 molar volume, there will be 10 to the power 20. Okay, let's say I am taking any material in 1 centimeter cube. If I am taking 10 to the power 20 number of atoms would be there, and corresponding to those atoms, those many number of electrons would be there. So all those electrons will be contributing to my final intensity. So this IE, whichever I am writing, always remember this is the intensity by a single electron. And if question comes that how the intensity is so low but we are getting in reality high intensity, here you have to explain that there are so many electrons which are present in a molar volume or in a single space. Those numbers, when you can see 10 to the power minus 26 it was there, now it has come to 10 to the power into, when you multiply this 10 to the power minus 26 into 10 to the power 20, now the suddenly you will be getting 10 to the power minus 6. Then similarly many molar volume if you consider, you will be getting high intensity. So this is the reason why we get high intensity in our X-ray analysis. And another factor, another interesting thing also to note from Thomson's equation. What do we have to note here? Here I always said in the previous class I have said that if you remember, then we have drawn one scattering center, and then in the scattering center how the scattering happens in atom. There I have considered the scattering center, and in this class also I am repeatedly saying my scattering center would be electron. Why not proton? Why not neutron? Because eventually, let's say this is my nucleus and electrons are here. So when the X-ray is coming and it is getting scattered here, why not electron? Why not neutron? The reason lies in this Thomson's equation. Why? Because here mass of one electron, okay, it is, if you consider mass of proton, 1836 times lower than the mass of proton. So you can imagine 1836 times lower than the mass of proton. And similarly same things for also neutron. So here the M lies in the mass of the scattering center, it lies in denominator. If it lies in denominator, then the mass of proton, if you talk about, then the mass of proton will be 1836 times mass of electron. You have to not only just put the mass of electron, but you also have to put 1836 square in the denominator. Then in that case the value will be extremely low, right? So this is the reason from now onwards, whenever we are considering that our scattering phenomena is taking place or our diffraction phenomena is taking place, even though we are saying that this X-ray is getting diffracted from a gold atom, this X-ray is getting diffracted from a silver atom or a copper atom, nickel atom, that means we are eventually saying, or we are eventually considering that the reflection or the diffraction or the scattering which is happening, they are happening due to the electrons in those atoms, right? So even though I can say that in the previous class in the Bragg's diffraction, when I told that this is an atom, my X-ray is coming incident beam and this is my reflected beam, this atom means the diffraction or the scattering which is happening, they are happening due to the electrons only. Because if I don't consider the electrons or if I start considering my protons and neutrons, then the intensity which I will be getting from proton and neutron would be extremely low, right? So now we have, so this concept we have seen in the previous class, but sequentially since we are going, so in the previous slides what we studied, first we studied about the incoherent scattering, then we studied about the coherent scattering, that or the scattering by a single atom. Now in an atom, scattering by a single electron. Now in an atom, as we know that there is not a single electron present, there would be many electrons present based on the atomic number. So what will happen in that case? This this diagram we have drawn it previously. I'll just draw it again. Let's say this is x bar and this is y bar. Okay, so here my incident X-ray beam is coming, whose unit vector is S0 here. Okay, and the wavelength of this incident beam is lambda, right? And here also, after scattering, the wavelength does not change. Why? Because I am now considering coherent scattering. So in coherent scattering, the wavelength will not change, only the direction will change. So now we will see how the interference of the two waves happen when they both are scattered by two different scattering center. So here one electron is there, here another electron is there. Now you can see this is my incident beam, and if they are to consider, if I try to calculate what will be the phase difference. Why phase difference? Because my path difference will give me the phase difference, and my phase difference will give me interference, whether it is constructive interference, whether it is destructive interference, or whether it is partial interference. Okay, and from interference, what I will get? From interference I will get amplitude, and from amplitude I will get the intensity which my detector can detect. So if I am to consider the path difference at this point, x bar point, then here I can see that there are no path difference between wave 1 and wave 2, right? Because both of them are traveling same distance. Here they are traveling same distance, here they are traveling same distance, as well as here also they are traveling same distance. There is no path difference is there. However, if I try to put my screen or my detector in this region, that means in y dash region, then what will happen? You can see from this wave, let's say this is 1 dash, this is 2 dash. If I am talking about, then I can see that the amount of path traveled by the ray 1 dash is not same as the amount of path traveled by the wave 2 and 2 dash. Why? Because I can clearly see there is a path difference is there, and this, if I am taking it as my perpendicular, if I am drawing my perpendicular, then the path difference should be given by how much path difference I am talking about? AD will be the extra path here, because till AC the wave till this front, I can see both of my waves are traveling same distance. After this I can so beyond this path, beyond AC, both of my waves are traveling same distance. Similarly, after BD, both of my waves are traveling same distance. So whatever extra distance if I have to calculate, that distance is BC, this distance, and AD. Right? One is BC, another one is AD. So how we can, and this is the central nucleus, and nucleus has, so this does not give us any interference. This does not give us any intensity because of its heavy mass. So here this is the nucleus. If I am talking about R vector, then I told that the path difference, how will we calculate the path difference when we are talking in terms of vectorially? So vectorially, the path difference should be given by the incident wave vector. If you remember, a small k we have defined, that means the unit vector in that direction and the position vector, right? Same thing we can do it here. Now let's say the incident wave vector here, in the incident wave, whatever we have chosen, this is S0, and here the scattered wave vector, the unit vector of the scattered wave, what have we chosen? The S, right? So if we can see that the path difference will be AD minus BC. Why this minus is coming? I have told that we are taking the position vector in the opposite direction, right? So AD minus BC, AD how much it will be? So R, similarly, what will be the unit vector? Unit vector in terms of AD will be S dot R. R is the, let's say, radius, okay, from the nucleus. Similarly, minus BC will be, in this direction I am considering BC. BC is associated with the incident wave vector, because here the wave is still not scattered. So BC will be S0 into R, right? So this will be my path difference when I am trying to get the amplitude relation, when I am trying to get the intensity relation. And here you can see same thing I have. So this I have put it in the vectorial notation. Here S0 is, this is my, in this direction my incident beam is coming, in this direction is my scattered beam is going. And now if I calculate another vector, which is Q vector, that Q vector is called as scattering vector. So S0 vector is known as incident vector, S vector is known as scattered vector, Q vector is known as scattering vector. So this is how this is the vector diagram. Okay. So now I have defined all these things. Now if I want to calculate the phase difference, why phase difference is necessary? Because to see whether constructive interference or partial interference happening or destructive interference is happening. Now here at this wavefront x naught completely constructive interference is taking place, but since some path difference is there in y naught wavefront, we will know that here not completely constructive interference will not be there, the partial interference will take place and the path difference will be AD minus CB. So here when we are talking in terms of the phase difference is 2 pi by lambda into path difference, right? So phase difference we have defined is equal to 2 pi by lambda into path difference, right? So here the path difference is AD minus CB. Here we have written 2 pi S dot R minus S naught dot R. So here we can write 2 pi S dot R is what will be the S dot R? Here we can write S minus S naught dot. So remember here what I have done in this expression, in the between this expression and this expression, we can note one difference. What is the difference? Difference is lambda is here and lambda is not here. Why the lambda is here? Because I have told that k is the unit vector, but if we want to define a complete vector, then that unit vector will have some, let's say this is capital K, this is small k, then this is my unit vector and my some amount of magnitude also I have to give. So a vector is completely characterized by a unit vector and a magnitude, and then my magnitude is 1 by lambda. So here if I am taking my magnitude is 1 by lambda, I can take this thing inside and then I can write it in vectorial form. Okay, so this is my expression, final expression, and 2 pi S minus S naught from the vector diagram, from here the vector diagram, when I am calculating S minus S naught, it is coming as Q. So that is why I have written it here 2 pi dot Q 2 pi Q dot R, and Q is my scattering vector, and the scattering vector, what is the amplitude of the scattering vector? So if you put, and since this magnitude is 1 by lambda, this magnitude is 1 by lambda, so these two will be equal, right? And so that is why if I do draw a perpendicular to a point, let's say D, we will get the value as 2 sin theta by lambda, and this is how we have defined our scattering vector. And the in the diffraction condition, this is the scattering vector that we are talking about, that when the scattering vector will be equal to the reciprocal lattice vector, then only our condition for diffraction satisfies, right? And now what I will do, so far what we have seen the intensity by scattering due to a single electron. Then what we have seen the intensity by scattering from let's say multiple electrons. There are two different electrons are there, and due to what will be the we will see what will be the intensity. How we will see intensity? Because we have calculated the phase difference. So now let's say this is one wave I am talking about. Why I am talking in wave? Because to calculate my intensity, if I am talking in wave form, then I can take the it will be mathematically convenient for me. And when I am trying to calculate the complex conjugate of that wave, then the I factor will not be there, and I will be eventually getting the only amplitude. So that is why I am taking wave. Let's say Z1 is one of the wave and Z2 is another wave. And between Z1, how I am defining Z1? A into e to the power 2 pi I nu t plus phi. Here the t, that means I am defining my wave in such a way that at any point t I can get my get the position of my wave, and A here is the amplitude. I am talking about my initial amplitude. Here 2 pi I have defined. Nu is the frequency of this wave, and phi is some amount of phase shift. I don't know what that amount of phase shift, but since I am talking about the coherent scattering, I know that phase shift, whichever I am going to talk about, it will be constant throughout my all scattering phenomena. Similarly, J2 if I am taking, I am taking same amplitude e to the power 2 pi I nu t phi. Here I am adding another term. Why I am adding another term? Because between these two waves we have seen that some amount of phase difference would be there, right? So if I have to calculate the net or the net amplitude for the partial interference to be to happen, then I am adding here some amount of path difference, or delta is the total path difference I am adding. When it will be multiplied with 2 pi delta, it will be the phase difference. So now what I will do, I will calculate what is the interference effect when two scattered waves are observed in this front, y front. I will see. So what will be happening, and since I have taken two wave vector, then we know that vectors are, we can add those vectors, right? The resultant vector will be the sorry, the resultant vector will be the summation of all those vectors, right? From the vector rule we know that. So I am just adding z1 plus z2. So here z1 value is a into e to the power 2 pi I. This value I have put it here, and then similarly this value I have put it here. Now you can see one common thing. If I take a e to the power I nu t plus phi, from both of these things I can take a common, right? That's what I have done here. I have taken the common this thing. Now the expression will be 1 plus e to the power. So this thing I have taken out common, and here I can write, I am writing this term as here, that e to the power 2 pi I nu t plus phi, I can write into, since it is plus is there, I can write e to the power 2 pi I delta, right? That is what I have done it here. Okay, so this is the star I am writing. Okay, let's say double star. Here I am writing how I have broken it down, and since I have broken it down, I can write easily this term 1 plus extra term. I am writing it here. And if I want to, so now what is happening, there are two terms which are associated with it. This is one term, this is another term. The first term which I am telling, this term is present in Z1. That means my wave, let's say this is one of my wave and this is another of my wave. This wave has gone a phase shift or a path difference is associated with the Z2 phase. Okay, so a into e to the power 2 pi I nu t plus phi, this is a common phase which propagates through yy. That means it is present in both Z1 as well as Z2. However, this phase I am talking about, the second phase, it is present, it is coming due to the path difference, which is the path difference between the two phases, which is contributing to the phase shift or the phase difference, right? So this is a common phase which is present in both the phases, and this effect which we are getting, it is not due to common, it is not due to the common thing between the two waves, rather it is due to the phase shift which is ultimately coming from the path difference, right? So this is the when we want to submit, let's say I have taken two different waves, and at two different waves, what I am eventually getting, I am getting a common phase, I am getting a desired phase, right? But desired phase is due to the scatterers, common phase is due to their inherent wave property. Now if I am talking in terms of two scattering center, that means two waves I have defined and I am getting this effect. But what will happen, and yeah, this is for only two electrons, desired phase effect is coming only due to two electrons. But we know that our material or our atom is not made up of two electrons. Let's say for now we consider that our atom is made up of more than two electrons. What will happen if I consider n number of electrons in a material? Then in that case what we have to do, we have to submit means, let's say n number of electrons, that means effect of Z1, effect of Z2, effect of Z3, effect of Z4, all will be going some amount of path difference, and from path difference they all will be coming to the phase difference. And what I have to do to get the final Z, I have to add all of them, right? So n number of times I have to add all the effects that I am getting from the phase from the path reference, then all of the things I have to add. If I add all those things, then I will be ending with one of the equations like this: e to the power 2 pi I nu naught plus phi. This is common phase present in all the waves, and this is what I am getting all this. This is an interesting expression. Here you can see summation of fi e to the power 2 pi I into delta. So e to the power 2 pi I into delta, we know that this is coming due to the path difference. But then what is this Fi? This Fi is known as the scattering ability of a particular electron. It is not necessary that all the electrons which are present in an atom, here all the electrons which are present in an atom will scatter in a similar way. It will depend on their position where they are staying. That means the Fi is given as, this is the scattering ability of an ith electron. Let's say, since it is Fi, I am talking about any random electron. If you take, let's say I am talking about the first electron, I have to see where that first electron is, and if I am talking about the second electron, then I have to see where the second electron is. So similarly, this Fi, remember, this Fi is scattering ability. Since scattering ability of each and every electron will be different, so Fi corresponds to the scattering ability of an ith electron. And when you multiply it with the path difference with like e to the power 2 pi I into lambda, then this total expression will be giving scattering amplitude of an atom with n electron, right? So this is what is total scattering amplitude of an atom with n electron with a scattering ability of Fi. Let's say my scattering ability of my first electron is F1, my scattering ability of second electron is F2, scattering ability of third electron is F3. Then that means F1 e to the power 2 pi I delta plus F2 e to the power 2 pi I delta plus F3 e to the power, similar expression we can write. Okay, and here what will happen, we have now considered what will be my final wave, right? What will be my final wave vector when I am talking about the interference. That means my scattering has happened, and from fully constructive interference, when partial interference is taking place. I have taken consideration, I have taken all these atoms which are present in all these electrons which are present in an atom, right? But now what I have done, I have assumed by default something. That means I have assumed that the electrons are inherently a round shaped particle with negative charge, right? I have assumed that much. But from the quantum mechanics perspective, if we have to assume, then electrons are not isolated atom, rather it is a distribution of negative charge, or you can say it is a cloud, it is a distribution like cloud around the positively charged nucleus, right, from a quantum mechanics perspective. So when I am talking about quantum mechanics perspective, so when here what I have done, I have simply put F1, F2, Fi I have written. So this the scattering ability of an ith electron I have taken. That means my electrons are 1, 2, 3, 4, this like this I have taken. But from quantum mechanics perspective, if I have to consider, then electron will be they will be around the nucleus or around the proton, like rho. Let's say the density would be rho. Okay, so electron density will be rho. They will be they will not be individual particle, rather they will be distributed over the whole in a spherical manner, right? And integrating the interference, you will get this kind of structure. Okay, Fq, if you take all those, so here this is the charge density and e to the power qr, and if you integrate those things, let's say I am taking, now I will just show you in the next slide how this integration happened. You need not to see or you need not to worry about that integration. I am just telling you how these things are coming out, all these things. So if I take, if I now consider the electron cloud density from quantum mechanics perspective, then I will get the total scattering ability of this of all the electron Fi, whichever I am talking about. This is the summation is there, right? So F1, F2, F3. So all of them combined, when I am getting, when I will be getting, or when I will be putting the integration of all those things around the spherical surface of a nucleus, right? dV means I am taking a small amount of area or small amount of volume, then the final amount will be given me to. This term is very much important. This is called as atomic scattering factor, or sometimes it is called as form factor, right? Why this atomic scattering factor is important, will know it in structure factor calculation. So what is atomic scattering factor? Atomic scattering factor is nothing but a summation of scattering amplitude of an atom. Okay, so summation of scattering amplitude of an atom, it's which is giving all the the summation of scattering ability of all the electron around a nucleus. That is what atomic scattering factor is. So if you want to write, so this is summation of all the electrons, all the summation of here I am writing scattering ability of all the electrons, ability of all the electrons around nucleus. Okay, so I am reading it again, summation of scattering ability of all the, this is nothing, all the electrons around nucleus. So this is what called as atomic scattering factor, right? So when we are talking like I have told you this in this expression, how this expression it is taking place, but when we are going into, let's say currently we are assuming that the electron distribution in an isolated atom assumed to be spherically symmetric. I am assuming those things from quantum mechanics perspective. So when we are assuming those things, here you can see this is a small amount of dV, right? Small amount of volume I have taken, and around that volume my electron density is evenly distributed or spherically it is symmetric. So when I do the integration over the entire volume, then finally I will get my FQ. FQ is given as atomic scattering factor. You need not to worry about all these expression. Here one thing we have to see, that is this expression. Here you can see in the integration expression there is a term called sin QR by R. It is something related to sin X by X, right? And we know that when X goes to 0, when we put limit, then this sin X by X value comes to 1, right? So what is this sin X by X value? So when this sin X by so this QR, when I am talking about, eventually we will see that the term will come to, this is a function of theta. Okay, so this sin X I am talking about, so here instead of X, here you can see sin theta. So you don't have to see all these things, only we have to remember that as Q is equal to 0, Q0 means what? Q means scattering vector, right? Scattering vector 0 means what? This is my S0, this is my S, this is my Q. Q0 means S0 is equal to S, right? That means when my Q is equal to 0, at that time only this expression, the sin 2 pi QR or divided by 2 pi QR, or this expression, this will go to its maximum value, right? So when this thing happens, this F which I am talking about now, atomic scattering factor, will be equal to Z. Okay, only at this condition. And when it is happening, Q is equal to 0 means all the beams here, all the beams which are coming like this, they will not be scattered in any of the direction. I will collect them at this point. That means there are no path difference and no phase difference. I will be completely getting a constructive interference, right? So here if I am talking about Q is equal to 0, all of my incident beam are giving me maximum interference. That means constructive interference I am getting, and I am getting maximum intensity in that case. So that in that case, all the here I have taken that I is equal to 1 to n, right? The summation I have taken, I is equal to 1 to n means 1, n number of electrons, right? So when Q will be equal to 0, all of, so F will be, let's say F will be F1 plus F2. Currently I am assuming that I have 5 electrons, plus F3 plus F4 plus F5, right? No other terminology is associated with it. So F5 means hydrogen, helium, lithium, beryllium. Hydrogen, helium, lithium, beryllium, boron. That means all of my electrons are giving me maximum intensity or maximum they are contributing to the maximum scattering factor. That means it is not any more scattering taking place, rather it is the beam is completely transmitting. So when Q is equal to 0, I will be, all of my electrons in my atoms will be giving me maximum atomic scattering factor, and that scattering factor will be equal to Z. And here why I am talking about Z? Because Z is the atomic number, and atomic number defines us how many electrons are there in my atom. If my atom has 5 if my atomic number is, let's say 8, that means in my atom 8 electrons are there. So in that case my F will be 8. So here what we know, that atomic scattering factor is a function of sin theta by lambda. Okay, from this expression, there are few points we can take note about. When q is equal to 0, my f is equal to z, and atomic scattering. So this is one of my key point, and this is another of my key point. Atomic scattering factor is a function of sine theta by lambda. Why it is important to me? Here you can see this is an expression. If you can go to any good book, they have derived the expression. But what is important for me is atomic scattering factor is a function of sine theta by lambda. Then why it is important for me? It is important because due to this. If only when my sine theta by lambda is corresponding to 0, that means whatever scattering it is happening all in the forward directions and the angle is 0. My value, if I am talking about a nickel, here the nickel is 28. Only at 0 when my sine theta by lambda is becoming 0 from this expression, right? I will be getting F is equal to 28. That means all the 28 electrons are giving me maximum intensity in forward direction without any scattering taking place. Same thing I can take say for the silicon as well. Only when it is 0, all of the 14 electrons which are contributing to my scattering, right? So and the curve goes like this, it is decreasing. Okay, so when this thing is taking place, what we can see the sine theta by lambda, as we can now remember, my lambda is constant because I am taking I am considering a coherent scattering, right? So when this lambda is constant, but when I am varying the theta, as I am sine theta by lambda, when it is increasing, this f value it starts to decreasing, and eventually this f value, when it starts to decreasing, my scattering ability of my atom, it will be eventually decreasing, and when my scattering ability is decreasing, I will not be getting any more net amplitude. That means my amplitude will be decreasing and eventually my intensity will be decreasing. And this is the region we can say that here you can see the sine theta by lambda. Just a comparison I want to give it to you. There are different types of sources I have told in the last class. One is chromium, cobalt, copper, molybdenum, right? Cobalt, chromium, you can see the molybdenum K alpha is 0.710. It is almost half of the copper K alpha line, right? But still we are using copper K alpha until and unless we have a specific use for molybdenum. We want to, let's say we want to penetrate more depth, we want to extract information from a little bit more depth than currently we are using from copper. We generally go for this copper K alpha. Why not go to molybdenum? Then why not even we go to even higher material? Because the copper K alpha will be so much low in that case. Why we are not going? The reason is when you are inherently, when we are monotonically going, increasing the metal and increasing the atomic number, the K maximum sine theta by lambda value is also increasing if you are coming from this direction. And what will happen when this is increasing? Here you see 0.435, this is 0.5586, this is 0.64878, this is 1.4. If I have to put it into graph, let's say for copper I am putting into the graph, sine theta by lambda is 0.6486. That means it will be staying somewhat close to, this is 0.5 and 0.6486, right? For copper. For molybdenum you see 1.407, the sine theta by lambda. 1.4 means it is somewhat around this one. Okay, so now if I have to use a copper, if I have to see that what value I will get for molybdenum as well as copper, you can see my intensity will be, if I am only considering this factor right now, okay, atomic scattering factor, you can see the contrast in the, for a particular curve, you can see who is giving me high scattering ability, okay, from which X-ray I am getting more intensity, because in that X-ray my scattering ability of every atom is also increasing. So this is also another reason to to look at when we are selecting any particular source for our material. So we should not randomly decrease our K alpha, but we also have to take consideration into sine theta by lambda. Okay, and yes, this is how this curve look like. So finally, I have talked about incoherent scattering, I have also talked about coherent scattering, but total intensity what we are getting, we are never going to get only coherent scattering. Incoherent scattering will always be there, and it will act as the diffuse background to coherent scattering. So this is your incoherent scattering curve. This small one is your coherent. This is your coherent scattering curve. This is your incoherent scattering curve, and this incoherent scattering is proportional to f square IE. What do you mean by IE? IE is the intensity by the scattering from a single electron. So IE, I will write it here repeatedly, 1 by r square into e to the power 4 m square c4. So this is one term, this is another term, 1 plus cos square 2 theta by 2. You should not remember IE as a single expression, rather you have to break down it and then remember. So 1 by r square is giving my position. This is a constant, 7.94 10 to the minus 26, the Lorentz polarization factor, and IE, I naught. Okay, so this is what I, and I coherent is directly proportional to f square IE. So that is why, since it is directly proportional to f square, the more my f is, f means atomic scattering factor. Atomic scattering factor means what? The summation of scattering ability of all the electron in my atom. So the more scattering ability will be there in my atom, the more coherent intensity I will get. So since this is directly proportional to the f square IE, and incoherent scattering is directly proportional to f. Okay, so that is also another reason. The incoherent scattering, you can see it is going, but since this is f square, so we are always getting more coherent scattering intensity than more incoherent scattering. Okay, and remember one thing, if you talk about the incoherent scattering from light element is more significant than okay, no, it is heavy element, sorry. So this is heavy element. Why it is more insignificant in terms of light element and heavy element? From light element, if you talk about, let's say I am taking hydrogen, helium, lithium, beryllium, I am talking about Z is equal to 4. So in this case, if I am trying to calculate I total, then f square IE. F square IE means 16 IE coherent scattering plus 4. I am talking about 4 IE in this case, right? So here this will give you the coherent scattering, this will give you the incoherent scattering. But if you, that means 4 is significant as compared to the 16, like it has some value. But if we are going to higher atomic number, let's say I am taking any atomic number, Z is equal to 40. So in this case, I total will be 1600 IE plus 40 IE. So as compared to 1640 will be not adding that much background or that much noise to the intensity of coherent scattering. Okay, so these are the two things we have to look at it. And now when we have calculated the intensity, so far we know that how the intensity is coming. Intensity, first the intensity we calculated from a single electron, then we calculated the intensity when two waves are interfere with each other from the electron, and then from two waves we calculated, from two electron we calculated, and we summed it over an entire atom which is having n electron. But when this incident X-ray gets scattered, whether it's constructively, different diffraction happens. Those diffraction are spot diffraction, ring diffraction, as well as peaks will appear. So what will happen in so spots, ring and peaks, what is the difference between those things, we will see when we will be studying about the diffraction from polycrystalline material and single crystal, right? But the characteristics of a diffraction peak, if I am talking about, so here this is, let's say, diffraction peak. Now if I am talking about, then X-ray diffractogram. Okay, so the peaks will be coming like, let's say like this. Like this peaks will be coming. This peak will not be that much intense, but like this peaks will be coming. And X-ray diffractogram is a plot between intensity and 2 theta. 2 theta means the position. Okay, so characteristics of a diffraction peak. So these are called as the diffraction peak. Okay, so these are called diffraction peak, and the characteristics of this peak is, it is defined by position at which 2 theta it is there. Then only we will be able to know about the peak. Then how much intensity it is there and what is the shape of the peak, right? So generally ideally we should be getting a single line, but due to different contribution of broadening contribution, we are generally getting a peak like this. Okay, so here this intensity is the maximum intensity, and the 2 theta position which we are talking about, so this is the 2 theta position, and this position is corresponds to the exact Bragg angle. However, even within a little bit deviation from the Bragg angle, we will be getting some amount of intensity. So that is why it will be there are lots of factors which we will see. Ideally our peak should be, so this is the ideal condition, ideal peak, but we will not get ideal peak because of there are different types of broadening effect which are taking place, and different factors which will be affecting our diffraction, the peaks. Now coming to the intensity, so here one thing is position and intensity. So one intensity is Imax, maximum intensity, another intensity is the integrated intensity. How much intensity that we integrated intensity means the area under the intensity curve. So if we want to calculate how much intensity is there, total intensity is there under the curve, so here we have to take a consideration. Let's say we have talked earlier about the scattering of an atom. Let's say I am just deriving, which I am just drawing a few diagram, just remember. So let's say I am taking a diagram like this. Okay, and here I am considering that in A1 direction, let's say in A1 direction, A2 direction and A3 direction, I have unit cell are M1, M2 and M3, and I am currently considering my the electric vector or the intensity which I am going to consider now from the amplitude of the electric vector. So I am considering, let's say, any of the crystal, because crystal is a 3-dimensional, right? Now we cannot talk about any more 2-dimensional. We have to practically think about the 3-dimensionality of the crystal. So let's say at any distance, here I am talking about at a distance where there is a cell is there, a unit cell is there, but from that unit cell in A1 direction, let's say in A1 direction, this particular unit cell which I am highlighting, I will just change the color. This particular unit cell which I am highlighting right now, okay, so this unit cell is present after M1 unit cell in A1 direction, A2 unit cell in M2 direction, M2 unit cell in A2 direction, M3 unit cell in A3 direction. Just I am considering that thing, right? And here when this incident X-ray is going, let's say this distance is R, I am talking about, this is the distance from the incident X-ray beam, and after this there will be my scattering will happen, and my detector I am keeping it here. This detector will be giving me about information about phase shift. Okay, so for now just you don't have to really do the derivation. I am just explaining it to you so that you understand. So let's say my incident beam is coming from here, this is the O, and in a particular crystal where this is my crystal, this blue shaded one, my crystal, it is lying in after M1 direction in M1 cell in A direction, A1 direction, M2 cell in A2 direction, M3 cell in A3 direction. So after doing all these things, and then scattering will take place, and here I am capturing the phase shift, right? So when I will be considering all these things, then what eventually what I have to do, I will be getting an expression like this. Okay, whether no, yeah. So I will be getting when I will be taking all the electric vectors in wave form. Here you can see I have taken all the electric vectors in wave form, and when I will be doing the derivation of all those things, after what will be the position of the vector after M1 unit cell, what will be the path reference or the phase shift after M2 unit cell in A2 direction, and what will be the position the path reference in after M3 unit cell in A3 direction. I will be coming up with a big expression like this. Okay, here you don't have to remember this expression. I am just showing it so that you know how this intensity expression, how we are calculating the intensity under peaks. So this is the method that we have to choose. And from here also, if we want to calculate, let's say this blue shaded one, if I want to calculate, then this blue shaded one also, I am just zooming it for now. Okay, let's say here, this is my atom is lying here in this crystal, in this unit cell also my atom can lie somewhere. So that is why I have to, if I have to calculate, then finally from here this is my O, from here this is, I have to calculate one vector, this is let's say Rx vector, this is my Ox vector, and this is my resultant vector. So this is my Rx vector if I am talking about, this is my resultant vector which is R vector. So this is how I will eventually calculate. I will take all this Rx into my consideration. This R is the position from the position of the unit cell center from my incident X-ray beam. So this is how I will calculate, and finally I will be arriving with an expression like this: EP is equal to summation of AE e to the power this complex equation, and here you can see M1, M2, M3, 2, M2, M2. So these are the, here M1, M2, M3 means it is the here what I have told it here, that M1, M2, M3 belongs to the unit cell in particular direction. What this capital M1, capital M2 and capital M3 means, these are the total number of unit cell in those respective direction. This is A1 direction, A2 direction and A3 direction. If I multiply them together, then finally I will be getting the volume of my crystal. Let's say we are now considering our crystal or our material is 3-dimensional, right? So for scattering from the entire crystal, all the scattered waves must be summed. So whatever till now we have done the scattering consideration up to in 2-dimensional. So if we have to consider the scattering by the entire crystal, then all the scattered waves must be summed from n atoms. That means n number of atoms are also there. Now no single atom is there, but now more number of atoms are also there, and all those atoms are also lying in different crystal. So when I will be doing that, I will be getting a complex equation like this. Here you can see from this complex equation, same thing. If you just look at this expression, all these things you just leave. Fn, we know Fn is the scattering ability of my particular nth electron, right? You don't have to worry about this. So here if you just look the right side of this thing, it is written e to the power, just e is here, okay, e to the power 2 pi I by lambda s minus s naught Rn m1 a1 m2 a2 m3 a3. Here I can separate it out. This expression I can write it here, e, I'll just write it in another color, e, this expression, this part I am writing e 2 pi I by lambda s minus s naught into Rn into e to the power 2 pi I by lambda s minus s naught into m1 a1 plus m2 a2 plus m3 a3. Right, I can similar, it's e to the power a plus b is equal to e to the power a into e to the power b. That's what I have done it here. Okay, so now I am getting an expression like this. Okay, so I will forget about this expression because this expression belongs to the unit cell. So if I have to now look at this expression carefully, what this expression is giving me, e to the power 2 pi I s minus s naught into Rn. So this Rn whichever I am talking about, so this is the Rn value. Okay, so I have taken it here Rx. So this is what the summation, I have to do it over the crystal, right? So summation is, term is already present here. So if I put this term and sum it up over the entire crystal, then I will be getting a term called structure factor. Okay, so the structure factor, this is the explanation for structure factor. Structure factor is nothing but when the scattering, the atomic scattering factor means what? Atomic scattering factor means I will be getting the summation of all the summation of the scattering ability of all the n number of electrons from single atom. But when there are n number of atoms are present, or n number of atoms in an unit cell are present, then what will happen? Then becomes the structure factor. So this structure factor is nothing but the summation of all the atomic scattering factor in lying in different unit cells. Okay, so so same thing here. So this is what the structure factor is, and here I have written the same thing. This expression, entire expression, I have written it here. I have just separated it out, so you can see it here. This is one thing, this is second one, this is third one. So M2A2, M3A3, M1A1, I have just multiplied it with. You don't have to worry about that. But this expression I have entirely taken it out and put it here as structure factor. You can see the amplitude is directly proportional to the structure factor. When I do some mathematical expression and all those things, when I try to simplify by assuming many things, then finally I will be getting this expression, and this is one of the most important expression, not in terms of the calculation, but in terms of understanding why structure factor is so much important when we are calculating our when we are indexing or when we are calculating the intensity in our X-ray diffractogram. So this is what we are getting it here. I will write it a little bit bigger. IP, that means intensity at any point P, if I am talking about, this is IE into M square. M is nothing, M1, here I have written M is this one, M1 into M2 into M3, so entire square. So M I am writing M1 into M2 into M3 if I am talking about. So this is M. So M square I have written. Now this is FHKL square. This is what the final intensity expression looks like when there are many number of unit cell in A1, A2, A3 direction. If we are considering these are the three coordinate system, then when there are n number of unit cells are present, and the scattering ability of all the electron will be different, and the summation of all the atomic scattering factor in that entire three-dimensional crystal will be given by structure factor. Okay, and since this structure factor is directly proportional to the square of the structure factor is directly proportional to the intensity of the peak, the more structure factor we will have for our material, the more intense peak we will be generating, right? So this will give us the expression for highest the area under the peak. So now what is structure factor? Structure factor determine the intensity of any diffraction peak for a given crystal structure. Okay. Okay, yeah. So this is what structure factor is, but now you will see how to calculate the structure factor. So here just let me write down this expression once again. FHKL is equal to summation of Fn e to the power summation of Fn e to the power 2 pi I by lambda S minus S naught into Rn, S minus S naught into Rn. So now this is our expression for structure factor, but how to calculate structure factor for in terms of, because these are the things I don't know about. S I don't know what is the intensity, what is the unit vector in a particular direction. S naught I don't know. Rn, what is, how do I define Rn, that also I don't know. So how do we calculate structure factor for a particular crystal system, that we will see now. So if I want to do it, let's say summation of Fn, right? I am writing the summation now. So e to the power, here I can put 2 pi I S minus S naught by lambda. I can write it into Rn, right? S minus S naught by lambda I can take it, and if I take S minus S naught by lambda, so here I can, so this is the scalar form I have put. Now I can put Fn e to the power 2 pi I, this S minus S naught, what is the direction? If I am considering that S is the unit vector, this S naught is S is a unit vector, S naught also is a unit vector, and the magnitude is 1 by lambda, then I can write it this expression. What I can write? I can write it as S minus S naught is always the scattering vector Q into R naught, right? If I want to put it in the scattering term, okay, so Q into R naught, I can write it like that, and this I can write it like Fn e to the power 2 pi I. Q, Q is, I know that for a diffraction condition Q is what, d star, right? So d star, how have I defined the d star? Let's say I have defined it as h into b1 plus k into b2 plus l into b3, and b1 b2 b3 are the coordinate system in reciprocal lattice. Okay, so this I can write h into b1 plus k into b2 plus l into b3 dot, that is dot product Rn. How will I put? Rn means the position vector of a particular atom with respect to the coordinate system. So Rn means I have to put position vector. How can I define my position vector? That means where I am keeping the material, that is in real space. So I know at which distance I can keep my, at what coordinate system I am keeping my material. Let's say I am talking in terms of real space, and real space I am taking it a1, a2 and a3, right? So what will be my coordinate system? hu a1 plus v a2 plus w a3, right? I can write it like this. Now since I know that it's a dot product, right? So dot product means fn e to the power 2 pi I. These things will be multiplied, h into b1 into u into u a1, h b1 into plus k b2 into v a2 plus l b3 into w a3. This is what I can write. Why I am not writing hb1 into like this expression? Why I am not writing? Because in dot product it will be 0. That is why I need not to like this expression, and this expression I am not writing. I am only writing this. Here I know that b1 is the coordinate system in reciprocal lattice and a1 is the coordinate system in real lattice. So how have I defined my real lattice versus reciprocal lattice? Here I have written a1 dot, if you remember the properties of reciprocal space, how I have defined. So this will be a2 into b2 is equal to 1, a3 into b3 is equal to 1. Putting all these property, how can I calculate? This is summation of fn e to the power 2 pi I. This thing will be hu plus kv plus lw. This will be my structure factor relation. Here, what do you mean by h? I don't know why it's not coming. So here, what do you mean by HKL? HKL is the plane, right? HKL is the Miller index of the plane, or the plane in real space, or since we have defined it HKL in the reciprocal space, the HKL are the number, the Miller indices number for the point in reciprocal space. HKL I have known, and UVW is the position of the atom in a particular crystal space, right? So this is what I am writing it here again. So this is summation of Fn e to the power 2 pi I Hu plus Kv plus Lw. So this is what you have to remember for the structure factor calculation. This is the only term you have to remember for structure factor calculation. You don't have to remember any of the other things, right? So if you remember this expression, then you can calculate structure factor for any of the crystal symmetry that is coming. Let's say I am talking about BCC. You don't have to remember what is the structure factor for BCC, what is the if you remember, then that's good. If you don't remember, then you can easily calculate. It's a matter of a minute. So BCC, I don't know what is HKL value, right? Because for me, HKL plane can be any planes, right? But what I know in BCC, I know the U. So these things I don't know, U, V and W. This thing I know. How do I know these things? That means the position of atoms in a lattice. If I am talking about a body centered cubic, then what will be the value for body centered cubic, right? If I am talking this term, this is X, this is Y, this is Z, right? When I am talking about, then in a BCC, where the atoms will be there, remember, now I am considering single type of atom. So let's say single type of atom I am considering. So where will be the atoms will be there? Here, here, here. All the atoms will be here, 8 atoms, and then finally one atom will be, let's say I am putting it somewhere here, right? BCC. Now you understood where the atoms will be there, but I know that the atomic position, the position for which this, okay, I'll change it to color. The scattering ability of this atom will be similar to the scattering ability of this atom. Why? Because they are repeated over a certain period. However, this atom which I am talking about it now, this is not similar. This does not sit in a similar position as these all atoms are sitting. Why? Because if I calculate the UVW for this atom, that let's say atom number 1 and atom number 2, then it will be different. What will be the UVW position? Let's say I am considering UVW for any of this atom, it will be, I am considering 0, 0, 0, right? UVW value for second atom. So I am considering this one as my first atom, okay, since it's in origin, and over a certain periodic repetition I will be able to get all these atoms, okay. The second number of atoms, if I have to calculate, what will be its position? It will be half, half and half, right? So these are the two different types of position where my atoms can sit in a BCC lattice, and due to the difference in position, their scattering ability might be different and they will be different. So these are the two combination, two position or the two values of UVW you have to consider while calculating the lattice, the structure factor for BCC. So here what do you have to do? You have to, let's say two things are there. So I will now consider F1 e to the power 2 pi I h, I don't know, into u. H into u is 0 plus k into v is 0 plus L into 0. So I have calculated for this one, right? Then I have to add another one, F2 e to the power 2 pi I h into half plus k into half plus L into half. This one you can do. So e to the power, this is 0, 0, 0. This total expression will be e to the power 0 is equal to F1, because this expression will be 1 eventually, okay. F1 plus F2 e to the power 2 pi I. This is h by 2 plus k by 2 plus L by 2, right? And finally what will be the expression you will be coming with? F1 plus F2 e to the power 2 pi I h plus k plus L by 2, right? This will be the eventual expression, and 2 will be getting cancelled. So you will be coming up with F1 plus F2 e to the power pi I h plus k plus L, right? Now that I have considered that the I am taking one type of atom, so F1 and F2, the scattering ability of each of the atoms will be same. So you can take here F1 is equal to F2 is equal to F. I am considering that, okay, but due to their position they will be giving different amplitude, okay. So if I am considering that thing, then F plus F e to the power pi I h plus k plus L, right? Here I can take F out, 1 plus e to the power pi I h plus k plus L. I can write this entire expression. So here I have to go to mathematics to solve this equation. Why? I have known that e to the power pi I, if I have e to the power n pi I, then the value will be how much? This will be minus 1 to the power n, right? So if I have minus 1 to the power n, if my n is an odd number, so minus 1 to the power n will be how much? Let's say I will write it here in this term, okay. So let's say n is equal, I am writing it here, n is equal to odd, so e to the power n pi I will be minus 1, right? If n is equal to even, then e to the power n pi I is equal to plus 1. Why? Because minus 1 to the power even is plus 1, right? So this value I will get. So if I have to put these terms into here what I have got, so this is I am considering as n. So if my n is even, I will be getting, let's say I am first taking, if my n is odd, then I will be coming with an expression f is equal to f1. If my m is my n is odd, that means my summation of h plus k plus l is equal to odd, then this term will be, entire term will be -1, and this -1, this one, it will be, so this will be plus, this is -1. I will be getting plus and -1 is equal to 0. Okay, if my n is equal to even, n I am talking, n means h plus k plus n, here h plus k plus l, this expression I have taken. So my f is equal to f. Now this term will be, if this is even, then e to the power pi I into even, that will be +1, this is 1. So this will be my 2f, right? So this gives me the condition for structure factor. This gives me the condition for structure factor for BCC. So what is the structure factor for BCC? This will be 2f when h plus k plus l is equal to even, or if you want 2n, right? This is 0 when h plus k plus l is equal to odd, that means 2n plus 1. So this is the reason in BCC h plus k plus l is equal to even, that means the summation of the indices of your plane will be coming. F means what? F means structure factor, right? And 2f means your amplitude, whatever you are getting, or the scattering amplitude you are getting from your atom or from that particular plane, there would be some intensity from that amplitude, and 0 means you are not getting any of the intensity from that plane, right? So this is the reason in HKL, when you are talking about a plane of 1, 1, 0, right? So when you are talking about a plane of 1, 1, 0, h plus k plus l is equal to even, that means it will be h plus k plus l will be even. So this plane will be coming in your diffraction pattern. If you are talking about a plane named 0, 0, 1, that means if you sum, so this plane is coming 0, 0, 1 is summing up to 1, so it is odd, and the structure factor will be 0. And remember, in the previous classes, previous slides, I have told that I is equal to directly proportional to f square. So if this will be 0, then your intensity will be 0. So this is what we have known for BCC. Similar things also we can derive it for FCC. FCC, if I just want to derive all these things, so FCC, where will be the atoms will be there? It will be here, right? And one atom will be here, another atom will be here, 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 right? Another one will be this phase, another one will be in this phase. So here in FCG there are 4 different types of atoms are there. One will be 0, 0, 0, right? Another one will be sitting in half, 0, half, 0, half, half. Then another one will be 0, no, 0, what will be half of 0, half 0, right? So when you put all these things into, let's say, fn e to the power 2 pi I h u plus kv plus lw, you will be getting an expression like f1 plus, say, I am now taking f as common, 1 plus e to the power pi I h plus k plus e to the power pi I k plus l plus e to the power pi I h plus l. You will be getting an expression like this. So the condition for HKL will be, so this will be plus plus, so you will be getting 2f when HKL are unmixed, okay, and 0 when HKL are mixed. What do I mean by mixed and unmixed? Mixed and unmixed mean either you will get that so you will get the planes which will be unmixed, means either completely even or completely odd, right? Mixed means the combination of odd and even. So unmixed means 1 1 1, 0 0 0, 2 2 2, 2 2 0, 2 0 0. They all are either completely even or completely odd. You will not get an expression or a intensity from a plane named 1 1 0, 0 let's say 0 2 1. You will not get this kind of plane. So these are the structure factor for both FCC as well as BCC. Okay, and then if we want to go to the diffraction in the polycrystalline material, so we want to go to the diffraction in the polycrystalline material. So here we will see that the sample is here in this we have kept our sample and the X-ray tube where the X-rays are coming, right, and the detector is placed here, and this circle where the X-ray tube detector is coming, this circle is called as the goniometer circle. Okay, and here we have used a flat sample, not perfectly focused, and this is the reason that we are getting always line bits in our material. And there is another circle, there are two circles always remember associated with a X-ray diffraction. One is goniometer circle, another one is a circle which corresponds to the X-ray tube, sample and the detector. So that circle is known as focusing circle. Okay, we'll see all these things in our instrument section, right? And there are different types of factors. Now we have seen the total intensity, how the intensity is affected by structure factor. So there are also different types of factors are available. One is means they also influence our intensity that we are getting from X-ray diffraction. One is structure factor, another one is multiplicity factor. So these 6 factors you have to remember: absorption factor, temperature factor, Lorentz factor and polarization factor. Many times these factors we write it as Lorentz polarization factor. Polarization factor. So these two factors many times we combine it, and then so effectively there are so absorption factor we have known that earlier, that when X-ray comes and the absorption, how the absorption takes place, right? So structure factor we have studied how the structure factor directly influence the square, and then we will see the multiplicity factor. Multiplicity factor is the number of equivalent orientation that a unit cell can have. Let's say I am talking about 100 direction. Okay, all of them will be giving me same amount of intensity, So if I have to take a cubic crystal, if I am taking one, if I am considering 111, then the amount of or the net intensity that I will be getting from this 111 will be same from 1 bar 1 for a cubic crystal I am talking about. I am not talking about a non-cubic crystal. So like this, in different symmetry the multiplicity factor varies, right? So 1 bar, all these things when I am talking when I am taking consideration into, so they will be equally contributing to my intensity, right? So whatever that means the number of symmetrically equivalent direction I am taking. So whatever intensity value that I have got, it is not that I am only getting intense when I am indexing. Let's say like this, I have indexed a peak, I am putting 111 here, right? If I am talking in terms of a cubic crystal, then 111 I am indexing, but this intensity I will be getting from all the family of planes that this 111 has. If I am talking, if my crystal system is cubic, right? So I don't have to write this is 111 and there is no separate provision for 1 bar 11, 1 bar 11, all these things I cannot write separately. But this peak, whichever I am getting, I have taken into account of all these symmetrically equivalent planes in the symmetrically equivalent direction. So here you can see HHH will be giving me 8. So HH0 will be giving me 12 and HHL will be giving me 24. So these are the numbers. Let's say 2 to 1 in a cubic crystal, I have to multiply the intensity factor by 24. Okay, incorporating all those things. So here I am writing it. This is the P. This is the multiplicity factor. Multiplicity factor. Okay. So this is the multiplicity factor, and now you can see I naught E4 e to the power 4 m square C4. These are the expression and this f square. So this is, you know, so what are these h and w? H and w related to the slit height and slit width. So, these we have put when we are taking calculation, when we are doing the calculation for intensity. We are also taking instrument part. So these are the slit height, slit width, all these things we have to, and this r is the position vector where we have to take consideration v u c, this value related to the unit crystal. But here another factor which we have to consider into this is the Lorentz polarization factor. I told you one is Lorentz factor, another one was polarization factor. So this is, yeah, Lorentz polarization factor here we have to take into consideration, and you can see, so this is 2 theta, right? So in 2 theta how the Lorentz polarization factor varies. Okay, as you here you can see, as you go higher in the angle, let's say generally we do an X-ray scan from 10 to 90 degree. As you go higher in the angle in this direction, your Lorentz polarization factor is eventually decreasing. So it eventually decreasing means what? The amplitude is also net decreasing, and the amplitude decrease means the higher angle you go, the less intense peak you will always get. So this is the reason, if you have observed, then always at lower angles, so if you are taking, this is 2 theta, this is theta, this is intensity, so always at lower angles the most intense peaks are coming. So as you go let's say to the higher angles, the intensity of the peaks are getting low. One of the reason is that atomic scattering factor f is proportional, is a function of sin theta by lambda. So sin theta by lambda also decreases when you go when the q value increases. So this sin theta by lambda also value will also increase, and eventually f value will decrease. So f value decrease means this is the atomic scattering factor. Structure factor value will decrease, that will add to less intensity. Here also Lorentz polarization factor will also add to less intensity, the decrease in the intensity, right? So this is one factor. Similarly, absorption factor, when we are talking about absorption, how the absorption is taking place. So here if we are talking, our beam is coming interacting with a small amount of volume here, then again it is getting diffracted in the Bragg's condition. Then if we are talking two angles, then if I have written, no I have not, okay. So this the taking consideration into all these things, like I is equal to, we know that I naught e to the power minus mu x, right? So if I have to take consideration into the path difference, and if I have to integrate it with the whole volume, then di will be equal to here I naught e to the power minus mu into path difference, I am writing it here pd, and if I have to write it over a volume, so I will write it dvs. So dvs is the irradiated volume, so the volume corresponding to this cross section. That means I am talking now in terms of 3 dimension. So when I am talking, so if I do this, then finally I will be getting an expression like I naught a1 by 2 mu. If I am talking that the absorption factor is, the linear absorption coefficient is mu, then finally I will be getting a structural. So this I naught is the intensity of my incident beam, and a1 means the cross section, eventually how much cross means when my beam is falling, it is not falling on a point, like, so beam is coming out of a cross section, and that cross section I have to know, and this 1 by 2 mu is the contribution for absorption to my final intensity equation. Okay, similarly if I talk that what is the effect of temperature, that means my atoms are not sitting in a rest manner, they are always vibration happening between them. Okay, the mean displacement might be 0, but since the vibration is taking place between them, there due to that also the intensity will be affected. Okay, so what will happen due to atomic vibration? These are the things that will happen, responsible for electrical resistance, responsible for heat capacity and transport. X-ray peaks are not sharp, and due to this structure factor and then Lorentz polarization factor, all these factor will do what? Or peaks will not be sharp, and the reduction in intensity will be taking place. Okay, and yeah, so what will be the reduction the factor that will be considered, so that will be e to the power minus 2m, and this 2m is considered as the m is considered as d by temperature factor or d by Waller factor it is called. So so this will be the value incorporated with my final intensity expression. Okay, and yes, this also reduce peak intensity and increase the diffraction angle. And what will happen when I when the temperature, when I take consideration into temperature effect, ideally I should be getting peaks like this only. So this is T is equal to 0, right? So then thermal diffuse scattering will be happening. So what will happen at T greater than 0? T greater than 0, I will be getting peaks like this. So broadening will be happening. So ideally I should be getting one line, sharp line, and now the broadening will be happening, and due to this broadening I'll be getting peaks like this. And add to that other factor like other factors which are there, absorption factor and all those things, if I add, then I'll be getting a peak like, and diffuse scattering will also now incorporate, you can see. So like that I will be finally getting a peak like this. Okay, and yeah, this is my final intensity expression which I will be getting, adding into structure factor, multiplicity factor, linear absorption coefficient, and this is volume of the unit cell of the constituent crystalline substance. When I add all these things, and this K naught here I have written, this K naught has taken consideration into Thomson scattering, cross sectional area, everything it has taken place here. This is the temperature factor, this is the absorption factor, this is the Lorentz polarization factor, multiplicity factor, and this is the structure factor, right? So these are the 5 different factors which we have to calculate, which we have to consider while calculating the integrated intensity for a special diffraction peak. Okay, and yeah, peak broadening also happens, and due to peak there are, means ideally we should be ideally we should be getting one single peak, but due to these different metallurgical factors we will be getting a broad peak, low angle grain boundary, small particles grain crystal, deformation if it is there, stacking fault or antiphase boundaries, then compositional inhomogeneity, and variation in large scale. All these will be contributing to the peak broadening. So that is why instead of a single sharp line we are getting a broadened peak, right? Yeah, so that means how much time? Oh, 7:58, it almost 8. So there are 5-6 questions are there. We'll be going through those questions quickly, and then we'll be finishing the session. So question 1 is, which of the following statement is or are correct for X-ray reflection of, just a second, NaCl according to the structure factor rules? Statement 1 is, peak intensities are higher for HKL having all even indices, peak intensities are lower for HKL having all odd indices, and peak intensities are 0 for HKL having mixed indices. So can anyone answer? I think NaCl has been calculated in the class. So you have to calculate structure factor. So what will be the structure factor for, let's say, if HKL I am calculating for NaCl? Can anyone, does anyone remember? Just a second. For NaCl structure, does anyone remember what is the structure factor?
Sir, D, sir.
Which one? D.
D, sir.
Yes. So for NaCl, if you calculate, say, now remember, I have already taken F1 is equal to F2 is equal to F in my earlier BCC FCC. Why I have taken? Because all atoms are same. But NaCl, what will be? Atomic scattering factor for Na will not be equal to atomic scattering factor for Cl, right? So that is why you have to write. So the value I don't remember, we have to calculate. I think it is FCl plus FNA. If I am correct, just calculate. Or so for even indices, and then this is for FCl minus FNA for odd indices, and this is 0 for mixed. Okay, so when you calculate all these things, I will be getting this. So that means for even indices, it is the addition of the peaks. For odd indices it is the subtraction of the peaks, and for mixed indices you will be getting a term 0. So all of them will be correct. Okay, so this is related to a crystallite size. We have not discussed in the crystallite size. So crystallite size is given by Sierrer's equation. Sierrer's equation, and crystallite size is generally defined by a term called FWHM. That means full width half maximum. I don't know why. Just give me a second. I'll just charge it. The pen is not responding. Just give me a second. So what is the answer? Has anyone calculated? I don't know.
Sir, A is the answer, sir. 135, sir.
Yeah, just give me a second. My laptop is running with low battery. Okay, so this expression I have not written earlier. So Sierrer's equation is given by FWHM is given by so generally this is okay, I don't know what is happening to my pen. Full width half maximum. So this we generally take it out from, let's say this is the intensity curve, and at half intensity what is the value. So this take it as theta 1 and theta 2 we can take, and then finally we calculate the FWHM value. So this FWHM, so the formula for this thing is k lambda divided by d cos theta, right? So here generally this is the Sierrer's equation. Here the k value varies from 0.8 to 1.2. okay, and this k refers to the shape factor of the k refers to the shape factor. Okay, and for spherical material, since we are assuming that our crystallite size crystallite are of spherical shape, for spherical shape only we can consider k 0.9. so that is why for FWHM you can put 0.9 into lambda divided by d cos theta, and here cos theta we know Bragg angle. So Bragg angle is known to us. D is the crystallite size, so you can calculate the crystallite size. I haven't calculated, but yeah, you can just put the formula and get the answer. Okay, so next we will go to the next question. Yeah, which of the following sequence of peaks will appear for an ordered FCC material? Okay, we can okay, for an FCC material we have known that the HKL should be unmixed, then only we will get the F of 2F, and then HKL if they are mixed then we will be getting 0 F value if I am talking about. So here which are not which are unmixed? Statement 3, 1 1 1 2 2, these are unmixed, right? And here are 1 0 0 1 1 0 1 1 1, these are mixed. right? So ideally the answer should be statement 3, ideally. But here what we have assumed that by default our materials are disordered material. Disordered material means the atoms will be occupying their random position. Though we have assigned them the random position means a particular atom will be let's say there are different types of atom, all those atoms will be sitting in a in random position. We can calculate their position vector, but they will be sitting in a random position. Ordered material means they will be assigned a position and there that position they have to occupy. So when those things are happening, when an ordered crystal is getting formed, then in that case what will happen, the ordered crystal we will get what we call it as in TM diffraction superlattice diffraction, not diffraction. So we will get this superlattice reflection we get, and these superlattice reflections are those reflections which are called as these are the forbidden reflections. So you remember some of the reflections are forbidden. Mixed zero means those reflections will not appear in our diffraction pattern. So these are called as forbidden reflection, and in an ordered crystal the forbidden reflection will be occurring. So 110, 200, 211, 222, they ideally they should not come in a FCC lattice, but since the forbidden it is an ordered FCC material, so all the forbidden peaks will also appear. So this is the reason. So statement 1, statement 2 both will be correct because of the appearance of all these forbidden peaks, the mixed peaks which are not supposed to come in a disordered material. So you have to see when the question asks about ordered material or the disordered material. We will see what is the order and disordered material when we are studying about the strain effect in the next class, when we will see strain effect and shape effect of the material. So yeah, this is the question, which are the correct difference between the polymer diffraction patterns and a metal diffraction pattern. Yes, can anyone? Broad peaks, high degree of orientation of patterns, presence of amorphous halo. So this is A, B, C and D. Can anyone answer? So polymer diffraction peak means there will be the mixture of amorphous and crystalline bond.
B option.
Yes.
1 and 2, sir.
Which one?
1 and 2.
D.
Broad peaks.
High degree of
Option
orientation.
B,
B
sir.
or D?
D.
Okay, mixed answer I got. So, okay, so metal powder pattern, when it is there, we will get actually all three. So presence of amorphous halo, because polymer is a combination of monomer, and monomers are, some monomers are crystalline, some monomers are amorphous. So when we get amorphous, some crystalline, due to the those crystallinity will not be very good, the crystallinity will be poor. So when we will get poor crystallinity, broad peaks will be there. That means our peak will not be sharp. And high degree of orientation of patterns, no, this will not get high degree of orientation of patterns. In a polymer diffraction we will not get high degree of orientation. High degree of orientation means all the crystallinity will be oriented in a single plane, right? In polymer we will not get. So what is the correct difference between polymer diffraction pattern, metal powder pattern? 1 and 3 should be the answer, but orientation of patterns, and this should not be the answer actually. The presence of amorphous halo would be the answer. So oh no, the answer is written, option is not there. 2 and 3. This metal powder pattern, high degree of orientation, it is for metal powder. So maybe considering this thing, the option would be D, but right now there is no option, so you have to write 1 and 3. These are the correct option. Okay, because high degree of orientation, if we are talking about, then we are talking about the crystallinity. Okay, Okay, and in polymer the crystallinity is 4. Okay, this is a this okay, this is the fifth question. The following statement is true or false. A laser beam is a focus beam of monochromatic light. True or false? Think in terms of point perspective, not do not think in terms of a sample perspective, whether it's true or false. We know that.
True, sir.
True.
That is why I gave the hint of point perspective, because a laser beam is a focus beam. Focused means, when I am talking about a focus beam, that means I am talking that it should focus on a point, a single point. Okay, so in this statement, if I am talking about there is a focus beam, then laser is not a focus beam, it is a monochromatic light. It's correct. That is what we have studied in optics, light optics. It's a monochromatic light, but it is not a focused beam. Okay, means the laser can diverge, means we can diverge the laser light. So it is not focused into a single point. It is even if we want to focus it, it will focus into an area. Okay, so from that perspective, if you think it is a monochromatic light, yes, it is a monochromatic light which we are using for in optics, light optics, light optical microscopy, but it is not a focused beam. Okay, so that is why this is false. Okay, yeah, this the structure factor of a crystalline material having atoms sitting at coordinates 0, 0, 0 is, can anyone calculate the structure factor?
Sir, yes, sir, yeah.
Yeah, that's correct. So structure factor is f, like where f into e to the power hkl e to the power 2 pi I h plus k plus l. When I am talking about f e to the power 2 pi I h plus k plus l, 0 plus 0 plus 0, so is equal to f into, this value will be e to the power 0 is equal to f into 1 is equal to f, right? So this is the correct answer. Okay, so that will be the, that completes our question today.